This is the second part of the video on survival analysis. And in this second part, we're going to talk about how we can compare survival between different groups. Well, actually, there are two ways for comparing survival curves or survival estimates. And the first method is comparing the actual Kaplan-Meier estimates or the Kaplan-Meier curves that we have seen. And we do that with a log-rank test. The log-rank test is a non-parametric test. That means that it does not make any assumption of the underlying distribution of the different times in which the event takes place. It just compares these event times between the two groups. The second way is using a Cox proportional hazard regression approach, a regression framework that will provide us with an effect estimate of how much the two groups differ in their survival. Let us look at a typical example. This is a study comparing two ways for the treatment of brain metastasis in patients who have a certain type of lung cancer. There is the group with chemotherapy and there's the group with an experimental drug. And what we see here is that for the group that use conventional chemotherapy, the proportion of people surviving in each of the time points is always lower compared to the proportion of participants surviving in the group with the experimental drug. And here survival is literally not dying. As we have said earlier, in survival analysis the word survival is used in a very broad sense as not having the event. But in this study, where the event was death, survival really means literally not dying. So the authors reported a log-rank test, and a log-rank test tells us whether or not these two curves differ. And like any other test, the null hypothesis is of no difference in survival curves. And with a reported p-value of 0.002, we need to reject that null hypothesis of no difference in survival curves. This is an important finding, but the log-rank test does not tell us anything of how big the effect is of the experimental drug compared to the conventional chemotherapy with regards to improved survival. For that, we're going to use a regression approach. In this case, the Cox proportional hazard regression. And it assesses the strength of association between the exposure and the outcome. So here, the type of treatment on actual dying. So in that sense, it is very similar to a regression approach, a linear regression and logistic regression, where we also use that regression to assess the strength of the association between group membership and the outcome. The difference here that it needs to deal with all these multiple assessments during follow-up that is so typical for the longitudinal study. And it also needs to deal with the fact that in all the different time points there can be a different underlying risk. So the way that the Cox proportional hazard regression works is that it estimates an average measure over the effect over the entire follow-up period. And that measure of effect is called the hazard ratio. And the hazard ratio indicates how more likely it is to have the event in one group compared to the other group. But calculating an average hazard ratio over the entire period of time only makes sense if that hazard ratio between the two groups stays more or less the same over the completed follow-up time. And that is what we call the proportional hazard assumption. It doesn't matter how much the risk is, as long as the ratio of the risk between the two groups remains more or less similar over this full observation time. Assessing this proportional hazard is very important for standard survival analysis. So the way to do that is that we can actually plot the hazards. And if we make sure that the y-axis is on a log scale, then we get not the stepwise regression, but actually we can see whether or not the two groups are having parallel lines. We can also use a formal statistical test called the proportional hazard test. We have to decide what to do if this important proportional hazard assumption is not being met, because it means that time is an effect modifier. It means that the hazard ratio differs between different time periods, and that is identical to time being an effect modifier, that there is an interaction with time. And like any effect modification or interaction, we can go for a stratified analysis. So actually we do not report an average hazard ratio, but we report multiple hazard ratios for multiple time points. Or we can actually, just like any interaction, take an interaction term into our Cox proportional hazard model itself. Either way would work. The important thing is that this proportional hazard assumption is assessed and acted upon if found validated. So how would it look like? So assume that there is a baseline hazard that looks something like this. And as you can see, this baseline hazard is not constant over time, with a much higher hazard in period 8 compared to period 1 and 2. The actual form of the baseline hazard is of no relevance. The proportional hazard assumption says something about the ratio between the hazard in one group and the second group. So we have to see if the ratio of hazards remains constant throughout the follow-up. So actually what we like to see is that if we put the hazard on a log scale, like done here, that these lines run parallel to each other. And I try to visualize this with the black arrow that is indicating the hazard ratio at time point 0. And we can see that it is the same size at period 3, and it is also of the same size of period 6 or period 8. So in this situation, although the baseline hazard has a very erratic form, indicating a lot of changing of the baseline risk, the ratio of the risk remains constant over time, comparing group 1 and group 2, the intervention and the no intervention group. So this is the typical when the proportional hazard assumption is met. We go back to the same study. We had already seen the logrank test, that it was significant, indicating that these two survival curves are not identical, that they are statistically significantly different. And now, with the Cox proportional hazard regression, we also can put an effect estimate. It shows here that the hazard ratio for the experimental drug group is 0.55. So the average risk over time of dying with the experimental group is 0.55 times that of the conventional chemotherapy group. So it means that the risk of dying over time is almost halved when using the experimental drug. So this is the end of part 2. In the last part, we're going to look at the actual time to event.